the last section. Pretty sure. Colloids. Colloid or a colloidal dispersion is kind of like a solution, but it's not a solution, really. It's a mixture in which you have a substance that is dispersed uniformly through the dispersing medium. But the difference here is that the colloidal particles are significantly larger than typical molecules. So they are small enough to stay suspended in the liquid, but they're larger than typical solute molecules. And so they cause this colloid to be cloudy because these particles are large enough to interfere with the transmission of light. You can't see them still, but they're big enough to deflect the light. So the colloid particles are typically a nanometer up to 1,000 nanometers in diameter. If we look at colloid particles under a microscope, they have a distinctive jittery motion called Brownian motion. Because these particles are large enough that they can be seen with a microscope.
What if you could do SEO smarter and faster? With Wix, you can edit your meta tags.
Yeah, don't care. Well, these are little pollen grains. You see how they're jiggling? They're jiggling because they're being hit by water molecules. We looked at this in an earlier lecture. Let's just close that before it goes off and does something else. Nope, we don't want to do that. Not this. So you can see the colloidal particles under a microscope, and we see that they're just kind of jiggling and gradually moving around because the water molecules have kinetic energy and they are moving around in the liquid water. So that's called Brownian motion after the guy who discovered it. If you have enough soap added to water, the soap molecules are going to form micelles, which are large enough to scatter light. And so basically then you have a colloid. So this is an illustration of a soap molecule. Most of it is this carbon-hydrogen chain, which is nonpolar, but then at one end we have two oxygens. And so this end is polar and the rest of it's nonpolar. So we call this the ionic head of the molecule. So when you put these guys in water, water is polar, this part is not polar. It doesn't get along with the water very well, right? So this is where you get the Swedish people and the Japanese people clumping together in the room. So all of the tails, the nonpolar tails of these soap molecules are going to gravitate towards each other because they speak the same language of nonpolar intermolecular forces. And the polar heads, the ionic heads, are going to stick out here because they're good at talking to the water. So it's kind of like circling the wagons to defend yourself against the wolves or something. So they'll make these spheres where the inside is all these little polar tails and the outside is ionic. And these will stay in solution instead of, like oil normally does, just making two separate layers. They're going to stay in solution because these ionic heads of neighboring micelles are going to repel each other. And then what happens when you're trying to wash your hands and get rid of especially greasy or oily things is this nonpolar interior will allow oil or grease molecules into it because those are also nonpolar. And then with the ionic heads on the outside, these little micelles of soap can carry away the grease. Anybody have any questions about that? Proteins can also form colloids. We call those macromolecules because they're really, really big. So these are some different types of colloids or colloidal dispersions, things that you might see in everyday life. Fog, we experience that pretty often, right? Fog is a colloid of water droplets in air. You can't see through the fog, right? Because the water droplets are large enough that it doesn't allow you to see. There is water in the air that we're breathing and looking through in the classroom right now. But it's individual water molecules in the gas state, and they're not large enough to block light. Smoke is going to be little pieces of ash suspended in air. This is my favorite colloid, whipped cream. So here we have air bubbles suspended in butterfat. Milk contains fat globules in water. Have you noticed that whole milk and skim milk are not quite the same color? Skim milk looks like somehow kind of thin or something, right? It's like it's trying to be transparent. Because what makes the milk white is those fat globules that are suspended in the milk, and they don't allow us to see through. Well, you take some of those out, you skim some of the fat off the milk, and now there's not as many, and so you can more see through the milk. Now, the fat globules are not the only thing, it's also milk proteins in there. And then opals are water suspended in silica glass. The Tyndall effect, if we shine a light through a colloid, we see that the light gets diffracted by the particles because they're larger. The light shining through a solution, the particles are too small to deflect the light, and so we do not see the light beam in the solution. And so this is a picture of a cathedral where we have light streaming in these windows, and we see these sunbeams, we call them. Why can we see that beam of light? Dust, right? You can't blame them. This must be really hard to keep clean. Little tiny pieces of dust in the air, and I know this happens in my house. If you go look at that sunbeam really closely, sometimes you can actually see the little pieces of stuff floating around in the air. But anyway, so that's showing us that this is actually a colloid. There's little suspended particles in the air. So the Tyndall effect is a test for, is this a solution or a colloid?